Okay, let's unpack this. Today, we are really diving deep into some, well, pretty dense material, but it's incredibly well put together. We're looking at these key excerpts on the postmodern unified theory, or UPT, from Leh Van Hull, specifically from energy dynamics work and UPT waves.
Yeah, and this is a fascinating one because it's not just scattered ideas. It's a complete system, a fully formed, mathematically closed framework. And it's all driven by energy. It defines how energy, dynamics, and mass intensity all hook together.
Exactly. So our goal here, our mission, is really to give you the fast track to understanding its core logic. How does UPT actually define its world? And maybe more importantly, how does it bake in its own stability? We need to find that central idea.
And that central idea, the thing we'll keep circling back to, is this unique connection it makes. See, UPT mathematically shows that the speed waves travel is directly, fundamentally tied to how easily the material itself can flow or diffuse, which is pretty different, right? Usually those are treated as separate things.
Yeah.
UPT says they're basically two sides of the same coin.
Okay, so let's start right at the beginning then. The foundation. What's the main variable, the main player in this whole theoretical setup?
Right. The absolute foundation is this variable other. The theory calls it mass intensity. And you should think of it maybe not just as density in the simple sense, but as the fundamental quantity that the theory uses to organize everything else. Its units are standard SI, the kilograms per cubic meter. Nothing exotic there.
So $dollar is our lead character. What are the rules it has to follow?
The biggest rule is conservation. Simple idea, really. If you add up all or over your whole space, your whole domain, that total has to equal the actual measured mass of dollars. That's a critical constraint. It means mass can't just, pop into existence or vanish. And the source material is very strict here. It locks a coefficient appa to 1. For simplicity, it basically says the total quantity is the mass.
I noticed that strictness about Capadon, but what does locking it down like that prevents? What does it force the theory to do?
It forces a kind of purity, I think. By setting kappa dollar, the quantity kia is just identical to the mass dollar. No wiggle room. So the theory has to focus entirely on how that one conserved thing, $, gets redistributed dynamically. Keeps things very focused.
Okay, so we've got $. Once we have that, we can define the energy state, the energy density epsilon, right? That's what the system's always trying to minimize. How's that built?
Exactly. The energy density epsilon is key, and the total energy is just the integral of epsilon over the whole domain. Now, epsilon itself has two parts, and they're conceptually really important. First, there's a basic part, kind of a bulk energy, that's just proportional to the dollar itself. Simple enough. But the second part, that's the really interesting bit. It's proportional to the square of the gradient of $.
Hold on, the gradient. So energy isn't just stored in how much intensity there is, but in how quickly it changes from place to place.
Precisely. That second term, it captures the energy stored in the variation, or you could say the slope, of the mass distribution. The source even calls this intrinsic tension compression. So if you have a really sharp boundary or a steep change in density, boom, you've stored potential energy right there.
And those coefficients, alpha and gamma, that are multiplying these terms, are they just there to make the math work out, keep the energy positive?
That's their main job, yeah. Technically, they ensure convexity. Gamma goes with the gradient term, alpha with the bulk term. They have to be chosen so that the total energy dollars is always 0 or positive. That basically guarantees the energy landscape is stable. It has a bottom.
Okay, so energy is like tension. We need something to release that tension. That sounds like where the state potential mimela comes in. How should we think about Lutro? What is it, conceptually?
Yeah, Junkers is maybe best thought of as an intrinsic pressure. It's the thing that tells the mass intensity where it wants to go, and it's derived directly from that energy density definition we just talked about. Technically, it's the variational derivative, which is just a fancy way of finding the direction of steepest descent for energy.
What's really striking there is that this pressure, it depends on the curvature of the intensity profile, not just the intensity value itself.
That's exactly right. The definition of Dummel involves the Laplacian of $. Remember that the Laplacian measures how curved a function is at a point, like whether it's part of a peak or a valley. So de Mulder includes the basic alpha term, but then it subtracts off something related to this curvature, $2 gamma nabla 2 Li. This means if dollars is sharply peaked or highly bowed, the potential dollar changes significantly. The system's pressure really cares about the shape of the distribution.
Okay, and this potential nullo, this pressure, it then drives the flow. Tell us about the main dynamic equation, how dollar actually changes over time.
Right, the core dynamic equation describes how all dollars redistributes. It says the rate of change of $8 over time, partial band is driven by how the mass current, day dealer, flows in or out. It's the divergence of Jailer. And that current, it flows down the potential gradient. Just like heat flows from hot to cold, mass intensity flows from high emitter to load up. So that feels intuitive.
Pressure differences make things move. And the Nollar in that equation, the mobility, what's that?
Not Nollar, the mobility is just a coefficient saying how fast that flow happens in response to the pressure gradient. If Nollar is really high, the system equalizes pressure differences very quickly. If Nollar is 0, well, then nothing flows. No matter how big the pressure difference is, the system's frozen.
And it's not just the intensity inside the domain that moves, right? The boundaries themselves can move.
Yeah, that's another elegant piece. The boundaries aren't just passive walls. They actively help reduce energy. The theory sets a rule for the boundary velocity of $5. It moves perpendicular to the boundary, and its speed is of normal mu, all ballers, another positive coefficient. So if the potential mu is high at the boundary actually moves inward. It shrinks the high-pressure region. It's the system's way of automatically trying to lower its total energy by adjusting its own container, basically.
Okay, let's connect the dots. We have energy. We have rules for how things move based on that energy. Now, the work law. That's about how the total energy dollar changes over time to seller. And since the boundaries are moving, you need something like the Reynolds transport theorem, right? It gets a bit complicated.
Exactly. The full work law accounts for everything. Work done by forces at the boundary, energy carried across the moving boundary, and the internal changes. It's complex, but this is where UPT really shows its strength, where it performs a kind of self-check.
Right, and this is where it gets really cool because the theory has to prove it makes sense, that it's stable. The source calls this calculation the energy dissipation box. What's the big reveal? What comes out of that box?
The reveal is the proof of stability, plain and simple. When you plug the dynamic equation for 1 hour, the one with Rowler, and the boundary movement rule, the one with $1, into that complicated work law, almost everything cancels out beautifully.
Okay, so what's left? What does des actually equal?
What's left is just the sum of two terms, both integrated and both guaranteed to be negative or 0. One integral is over the volume inside, and it looks like m lub U22. It represents internal dissipation, like friction from flow. The second integral is over the boundary surface, and it looks like m lub U22. It represents energy reduction due to boundary movement.
So the rate of change of energy is minus some internal friction term minus some boundary adjustment term.
That's it, exactly. And since the mobility dollar must be positive or 0, and the boundary coefficient dollar must be positive or 0, and squared terms like nobula mu2 and nu2 are always positive or 0, then the whole expression for dead dollar has to be less than or equal to 0.
Wow, so dead dollars always. The total energy can only ever go down or stay the same. That's incredibly powerful. It's like the system is designed to run downhill energetically. The definition of energy and the rules of motion automatically guarantee the system will settle down to a minimum energy state. It proves its own stability internally.
That self-consistency is really the core achievement here. It also means that if you want total energy to be conserved, you need very specific conditions. That's what Theorem 1 and the source points out, basically. A closed system with no leaks and no network done at the boundaries.
Okay, let's pivot slightly. We've seen the abstract proof of stability. What about things we might actually observe? If this mass intensity stuff is flowing around trying to minimize energy, surely that should create waves, right? Does UPT predict waves?
It does. If you look at small disturbances, like little ripples of delta Euler on top of some background state, the dynamic equations simplify. They linearize into something that looks very much like a standard damped wave equation.
A wave equation, okay. And the speed of those waves, what determines that?
But this is fascinating. The effective wave speed, let's call it its Smith Euler, isn't just some arbitrary parameter. It's square, 2 out of dollars. Now it turns out to be directly proportional to the product of $2 gamma and dollars.
Wait, let me process that. $2 depends on gamma times na dollar. So the wave speed is directly linked to gamma, which is about how much energy is stored in the intensity gradient, times nollar, which is how easily the intensity can actually flow.
You got it. That's the crucial connection. The mechanism for wave propagation isn't separate from the mechanism for diffusion or flow. They're intrinsically linked through the energy definition. If you change how much the material resists gradients, change gamma, or you change how easily it flows, change dollar, you directly change the wave speed. They're not independent.
That's a really different way of looking at it compared to many models. We should probably also quickly touch on discontinuities, real world stuff like cracks or phase boundaries where things jump suddenly.
Right. UPT handles those too.
Yeah.
If you have a sharp interface or a fault moving through the system, the theory imposes strict jump conditions. These are basically conservation laws applied right at the moving interface. They ensure that neither mass nor energy is created or destroyed as something crosses that boundary, and make sure the fundamental conservation principles hold, even when things get messy and non-smooth.
Okay, so let's try to synthesize this. Let's trace that internal logic one more time.
Sure, it all starts with the definition of energy, AE, specifically including that gradient term involving gamma. That energy definition determines the state potential, E theta mu.
Yeah.
The potential mu then drives the dynamics, both the internal flow and the boundary movement. And finally, those dynamic rules, when plugged back into the work law, prove that energy must dissipate, confirming stability. It's a closed loop.
It really is a remarkably self-contained structure. It's not just a collection of equations that seem plausible. It's an architecture where motion, stability, waves, it all flows logically from that one initial energy definition.
And don't forget the practical details emphasized in the source, sticking to standard SI units and that Kappa-Dawid constraint, keeping the focus purely on mass redistribution.
So bringing it back to you, the listener, what does this all really mean? Why should you care about this theoretical framework? I think it forces us to reconsider some fundamental relationships, especially how we think about waves.
Absolutely. The source makes it crystal clear. Wave speed C laws is tied directly to gamma, energy of gradients, and more mobility. Now think about what happens if mobility law is zero, if the material can't flow or redistribute at all.
Well, if null is zero, then the law is zero, so partial of zero. Nothing moves internally. And 2 would be zero too. No waves.
Exactly. If the system is frozen, incapable of diffusive flow, then according to UPT, the mechanism for these energy-driven waves vanishes instantly. So what does that interconnectedness imply? That the ability to flow and the ability to support waves aren't just related, they're fundamentally inseparable within this energy framework. It really challenges fields where diffusion and wave mechanics are often treated as totally distinct phenomena. Could a unified energy view like UPT provide a more complete picture? That's the power of a truly self-contained theory to make you rethink connections.